Hi, in case you haven't noticed yet, you're living in the universe, as well as everything and everyone around you. We're all living in the same universe. All except for, of course, me, because I'm not real. But where, or a better question, what did this universe come from? Well, it all starts with one very important cosmological event: the Big Bang. But what is the Big Bang? A hypothetical audience member asks hypothetically. Well, at around 13.8 billion years ago, all of matter and energy, along with the four fundamental forces, which were at this time unified into what is known as quantum gravity, existed in a singular, infinitely small point, known as the singularity. That infinitely hot, infinitely small point suddenly expanded rapidly, beginning our universe and sending us into what is known as the radiation era, due to the universe at this time being dominated more by radiation than matter. This period of expansion, known as the Planck era, only lasted 10 to the negative 43rd seconds. The reason for its name being the Planck era is that it fits within one Planck time. Planck time being a part of the set of units called the Planck units, which is a set of units used to describe a scale smaller than that of the quantum wavelength, and by extension, our own comprehensible universe. And it is created by redefining the base units of mass and length so that we may attempt to understand what happens beyond the walls of general relativity and physics as a whole. Mass and length are redefined so that c equals g equals h equals k equals 1, where c equals the speed of light, g equals the gravitational constant, h is Planck's constant, and k is Boltzmann's constant. We can then use the equation for speed, being distance over time, in order to solve for time, which is distance over speed. We can then apply this to Planck units, where we get 1 Planck time equals the square root of the gravitational constant times Planck's constant over the speed of light to the 5th, roughly equaling 5.39 times 10 to the negative 44th. This is crucial to understanding the start of our universe, because this is the smallest amount of measurable time in which modern physics and general relativity still hold true. When utilizing units of time smaller than these, modern-day physics concepts begin to fall apart, and therefore, in order to have the universe begin to evolve in a way that makes sense according to modern-day physics, the Big Bang will have had to have lasted 1 Planck time before beginning to evolve. That may seem a little confusing, which is fair, seeing how it's essentially just saying we have no idea what was going on for this amount of time, literally because we have no modern way to comprehend what could be happening for that period of time. A process known as pair production also begins within the Planck era, in which matter is directly created through electromagnetic energy, resulting in a positron and electron. The reverse process is also possible, where an antiparticle and particle annihilate each other, resulting back into gamma rays. The most crucial thing to understand from this period is that the universe is very much not infinite, and due to that, the smaller it is, the larger amount of pressure everything is under, and therefore the hotter everything is. It is then due to the universe expanding that it cools down due to a lack of that pressure. It is due to the universe expanding over time that everything becomes more cool, and the universe is now at a comfortable 10 to the 32 Kelvin. It is now that we have reached this temperature that we may enter the GUT epoch. See, as both temperature and density fall rapidly, the universe's temperature crosses the 10 to the 32 K line. And when that happens, gravity splits off from the other three forces, separating quantum gravity into gravity and the GUT superforce, consisting of strong, weak, and electromagnetic forces. An important event that also occurs within the GUT epoch is the epoch of inflation, a period of time where the scalar fields of the universe, which are essentially what defines the differences between the forces of nature, would be elevated, and empty space would find itself in a very unstable condition and would have acquired vacuum energy. This vacuum energy is responsible for the inflation of the universe, causing it to grow not in a single spot or in a single direction, but instead in all directions, everywhere. Think of it like this balloon here. expanding in all directions and from all places. Not one place nor one direction is being expanded more in. If that doesn't work for you, however, you can be like me and think of it like lots of space grenades creating space, exploding repeatedly over and over again, creating space in all directions. Because this takes place in the Gut epoch, it only lasts for an extremely short time, 10 to the negative 33 seconds about. The GUT superforce only lasts for a short time, and as the temperature dips below 10 to the 28th, the bosons that would transfer force between the electroweak force and the strong forces freeze out. And as the GUT epoch fades away due to the lack of transference between electroweak and strong forces, the quark era begins to take over. Inside of the quark era, the elementary particles were now in equilibrium with radiation, as the heavy and light particles were in thermal equilibrium. What this meant for the universe is at this point in time, protons and antiprotons were being created and annihilated at the same rate. This is very important because after this event, no more protons or antiprotons were created. This left us with a more matter-dominated universe compared to antimatter, and the small amount that's the difference between matter and antimatter is all of the protons that we have today. It is also during this epoch that the electroweak force freezes out. As the universe cools past 10 to the 12th Kelvin, a group of particles known as leptons find equilibrium. It is during the lepton era that we find that the only particles still left in equilibrium are the electrons, positrons, muons, and neutrinos. It is also during this era where the universe reaches 10 to the 10th K, where neutrinos stop working with matter, known as neutrinos decoupling. After the decoupling of neutrinos, when the universe reaches 10 to the 9th Kelvin, we reach the final epoch of the radiation era, known as the nuclear epoch, as diagrammed by me very neatly on this board behind me. The way this works is that due to the strong nuclear force being, well, stronger than the weak electromagnetic force over small distances, when a neutron and a proton get too close to each other, they bond, forming a deuterium, as well as releasing some energy. From here, the temperature was just right to where deuterons could be around for long enough to bond again and turn into helium-3, and then from there into helium-4. This is the process that characterizes this epoch, as it is really hard to get just the right temperature for this process, as too hot results in particles being flung off, and too cold has nothing happening at all. This last epoch only lasted around 15 minutes, and not all deuterium bonded into helium. In fact, it is still possible to find deuterium today, and if you do, you have come across a part of the past, as the only detectable deuterium not found in the center of stars comes all the way from the Big Bang. But sir, you forgot to cover the other two eras, the matter and dark energy eras. What an astute observation, my student. Surely there must be a reason for this. April Fools, I'm not going to explain them in detail. I'm just going to summarize them, you know? Ha, funny. Happy April Fools, you goober. Okay, so inside of the matter era, where the universe is dominated no longer by radiation, but now by matter, we have the atomic epoch, the galactic epoch, and the stellar epoch. The first of the epochs of the matter era, the atomic epoch, starts at 16,000 Kelvin and is when matter begins to dominate. Atoms begin forming and electromagnetic radiation decouples. Then, during the galactic era, large-scale structures form, the first stars and quasars appear, and galaxies begin to show up. Finally, in the matter era, we have the stellar epoch, which is the one that we are currently in. Galaxies begin to merge and evolve, star formation is at its peak, and dark energy is starting to dominate. But sir, how do we know if any of this Big Bang Theory stuff is true? Because after all, it is a theory, and that you should have evidence. for that. Yes, you are quite correct, student. In fact, there is evidence, and the biggest form of evidence is the cosmic microwave background, which is leftover radiation from the Big Bang, which is detectable with radio telescopes. In conclusion, we've learned a lot about the cosmological importance of our past and our beginnings, and answers some of the biggest questions of humanity of what are we, where do we come from? This is way too serious. But hey, that's just a theory. A Big Bang theory. Thank you for watching.